Welcome once to the Calculus channel. My name is John Gabriel, and today I want to talk with you about 6 reasons why the mainstream derivative in calculus is flawed. In other words, the definition that you normally see. So let's begin. Now, I had an email exchange with a student of mainstream mathematics who asked the following questions. His questions are in blue font. My responses and answers are in green font. Formulas are in black. I first wrote that if we write the difference of these two expressions, f of x plus h minus f of x over h and L, if the absolute difference is less than epsilon, then this means that the distance between the non-parallel secant line slope and L becomes smaller as epsilon becomes smaller, or rather as the distance given by that difference can be made smaller than any given epsilon greater than 0. And it's important that it's greater than 0, and you'll see why in a moment. So the student says this is what they call the rigorous definition, right? And essentially, yes, this here is what they call the rigorous definition, okay? This. So it's normally stated in first order logic as for all epsilon and delta greater than 0, there exists an epsilon greater than 0, such that if the absolute value of this difference, x and h, is less than delta, this implies that this difference is less than epsilon, okay? And this is the main definition. So it's not really a well-formed definition, but a weakly stated property of this type of limit. So each limit has, in its own right, a different definition. So it's unremarkable and problematic for several reasons. So let's begin seeing why with the very first one. The definition is circular. So why is it circular? It's circular because in order to use it, one must know the value of L. Now remember, here is L in the definition. But we don't know L until we've worked with this finite difference here, until we've worked with this finite difference. Yeah, and we've reduced it to a form where we can see what is the derivative, namely the expression that does not contain any factor of h, okay? So don't worry, I'll give you a link to this article and you can read it and study it in your own time. So this is also known, this expression here is also known as the first principles method. That is, f prime of x, the derivative, or L, is used in its own definition, as you see over here. So L is the guess, but it has to be the same as the derivative if you want this very definition to work. Okay, so our very definition is a portmanteau, by the way. Okay, it's a portmanteau of verify and definition. So the second reason is that there is no such thing as a real number. Okay, that is, no valid construction. And none of Dieterich Katz's equivalent converging sequences, also known as Cauchy sequences, or Eudoxus reals, or anything else that you've heard about is valid. There is no such thing as an irrational number, hence no such thing as a real number. By definition, pay attention, a number is a name given to a measure of a ratio. In actual fact, it measures the antecedent magnitude of a ratio using the consequent magnitude of a ratio. Okay? And in algebra, it becomes standard through the abstract unit, whose size is irrelevant. In other words, the unit it acts as a sort of a consequent, but its size doesn't matter because all the properties are transferred. So the so-called definition, as I've stated, is a portmanteau, and it checks the guess L, which is derived from this Cauchy calculation where you find the derivative using this first by dividing by h and then saying that h cannot be 0, but The problem is that after you've done the division by h and made the simplification, taking the limit is equivalent to setting h is equal to 0. Okay, I don't care what anybody tells you. If you divide by h before thinking of it as not being 0 and then taking the limit, you are in fact doing exactly that very thing, setting h is equal to 0. Now some might retort that it's just a convergence sequence like you see here. For example, the limit L itself is not contained in the sequence of finite differences, and nor can ever be contained, by the way, because there is no finite difference of this form. In other words, with any hi, no matter how close to x, which will ever be equal to the limit in terms of the function f, only in terms of the tangent line to f at x. Now, my new calculus solves this problem rigorously for the first time in human history. Moreover, my historic geometric theorem gives you a way to understand this with complete rigor and have the same results as your mainstream calculus. Now, point number 5 is, in order for the very definition to work, it must be possible to have a hole at the point of tangency, and I've explained this to you in numerous videos where I've said wholly functions from old, etc. And this is mandated by the requirement that both epsilon and delta in the inequality, they call the definition, in this definition here, both of these must be greater than 0. And in order for them to be greater than 0, it must be possible for a hole to exist in the function at the point of tangency. Okay? So this is mandated by the requirement. And finally, the last reason is that my historic geometric theorem exposes a fatal flaw in the reasoning of mainstream math academics. If one takes the limit of both sides of this identity, it turns out that only one of these constants, and by the way, they're all constants for any given non-parallel secant line. You can't just decide you're going to change this one, leave this one constant and that one, because then the identity is no longer true. And we know that a theorem is called a theorem because it's true, not because it's false. So if one takes the limit of both sides, it turns out that only one of the constants, namely the slope of the tangent line, f prime of x, remains the same. This constant here disappears or becomes 0, and this here magically becomes the derivative. Okay, and the student asks, how is this definition significant? Well, it's a testament to the utter failure, incompetence, and grand stupidity of mainstream academics since Newton to realize a rigorous formulation of calculus. There is nothing rigorous about this definition here, and there never was anything rigorous about it. It's always been flawed. Okay. The student then says, so there is nothing one can do with it because there is no mathematical operation known as become smaller. That's correct. Mathematically, become smaller, tends to infinity, etc., are all meaningless phrases that lack any of the characteristic that is known as rigor. So the student also makes this comment here where he says it is understood what is signified and needs to be done, whether one sees any of these operators, the basic 4 operators of arithmetic. However, there's nothing one can do with lim h approaches c, because h approaches c, or the distance between c and h becoming smaller, is not a mathematical operation. Okay? And hence the rigor is nowhere to be observed. My response here was, to mainstream academics, become smaller means c closer to h, but that the absolute value of the difference c minus h can never actually be 0. So for this reason, the whole feature, as previously mentioned, is required. And of course, the student's reasoning is correct. And this is why I say, not anybody else, I say, there is no valid systematic way of finding a derivative in mainstream calculus. But fear not, I have prevailed. I have given you the new calculus, and I have also given you my historic geometric theorem. So my statement is true for all the reasons I've given you. And another significant reason that I've mentioned before is that taking the limit of constants are the constants themselves. This is even true by mainstream understanding or decree. The limit of the constant is always the limit itself. It can't change. It cannot change into something else. Okay? So, as I've explained, that none of the infinitely many finite differences here, even if the limit is a rational number, none of these finite differences ever represents the limit, even if it's a rational number. Okay, and rational is actually redundant, because when we say number, it means that it's rational. There is no other kind of number. So the mainstream formulation is a fraud, whether it's sincere or otherwise understood. And finally, the student ends up with this response to me: thanks. And you can read this response yourself. It's very, very telling. I would strongly recommend that you do that. My name is John Gabriel, and if you haven't already subscribed to my channel, become a subscriber, spread the news, and tell everyone you know about this best math channel on the web. And please feel free to contribute dollars or credits on my Odyssey channel. Till next time, this is a New Calculus channel, and I'm John Gabriel. Goodbye.